Okay, we're going to move on into chapter 17, section 8, and it deals with Gauss's law. Gauss's law is an alternative to Coulomb's law in determining the electric field. It's very useful for extended surfaces, extended charge distributions. And really, once you start doing physics with calculus, Gauss's law is one of those really beautiful things. We're not quite there, but I still think you'll see some of its usefulness. First, though, we have to introduce an idea of a new quantity called electric flux. Now, the symbol for electric flux is Greek letter. That's a capital Phi. Well, later we'll talk about magnetic flux. So I'm putting the little e there just to remind us that this is electric flux. And it's essentially the product of the electric field strength times an area times cosine of the angle between them. Now, to remind ourselves what everything means, E, of course, is the electric field strength. A is area. And phi is the angle between the electric field and a normal. Remember, in physics, normal means perpendicular to the area. Now, I think it'll make sense if I draw some pictures. Suppose that we've got a rectangular area like this. Okay, and coming through that, I'm going to draw the electric field lines in blue. We've got an electric field, and the electric field is pointing to the right. So we've got a variety of these electric field lines. Remember, the lines just help us visualize the strength of the electric field coming through this rectangular area. I also want to draw the normal. I'll draw the normal in red. We picture a normal segment. A normal segment is perpendicular to the rectangular surface. So it's at a right angle. In this case, the normal segment points in the same direction as the electric field. So our flux would simply be the electric field strength times the area times cosine 0. We all know cosine 0 is 1. So in this case, it's just E times A. This, in fact, is a way, this is kind of the maximum flux orientation, if you want to think of that. Now let's consider that same size rectangle but we're going to rotate it. So now the normal segment points this way, and our electric field points this way. Notice we may not get as many lines of the electric field through because some of them that would have passed through it when it was straight are going to not pass through it now. Okay, so now let's draw an angle here. So here's our angle. That's phi. It's the angle between the electric field and the normal. So it would be EA cosine phi. And then finally, we can picture a scenario where we actually rotate our surface like this. Now if I draw my normal, the normal would actually be pointing up. Again, remember the normal is always perpendicular to that area. And the actual electric field lines all still pointing to the right. I'm going to draw kind of a dotted one that's kind of underneath here. But none of them would actually intersect the surface, right? You cannot intersect a flat plane. It doesn't have any width. So in this case, when we do that the flux is EA cosine, in this case the angle's 90. Cosine 90 is 0, so the actual flux is 0. There would be no lines of electric field that would penetrate through a surface in that direction when it oriented in that direction. Okay, so that's what electric flux is. A flux is this product of the electric field strength and the area multiplied by cosine phi. So it's that part of the electric field that is actually perpendicular to the surface. The electric field that's parallel to the surface does not contribute to the flux. Let's do an example. Calculate the electric flux through a disk that has a radius of 0.10 meters. It makes an angle phi of 30 degrees, and the electric field strength is 2.0 times 10 to the third newtons per coulomb. Here's our picture. So we've got the electric field lines, and they're all pointing this way. Remember, this is our electric field right here. And then our disk is kind of at an angle. So picture this circular disk such that our normal to that surface, here's our normal, happens to make an angle here of 30 degrees. So it's not the surface itself that's at a 30-degree angle with the electric field, but it's that normal segment, that perpendicular segment. I often think it's almost like we stuck a handle on the area. So there's our normal right there. So in this case, our flux, EA cosine phi, is going to be 2 times 10 to the third, or 2,000. The area is a disk, a circular disk, so our area is pi r squared. So times pi times r squared. That's simply the area of a circle. And then cosine 30 degrees. Put it in a calculator, and I get 54 Newton meters squared per coulomb. Our units here, we didn't talk about units. Electric fields are newtons per coulomb, and then of course areas are meters squared. So our numerator is newtons times meters squared, our denominator is coulombs. So there is our electric flux. Now, remember, we rotate it so that phi is equal to 0. That's going to give us our maximum flux. That's going to be 2,000 times pi r squared, which is pi, times cosine 0. Cosine 0, of course, is 1. So that actually gives us a larger, that gives us a flux of 63 Newton meters squared per coulomb. If we rotated it again, and we let, and I really, let me change that. That should have been a lowercase phi. If we rotate it again, so that phi is equal to 90, remember that would mean no lines of flux. That would give us a flux of 0. Cosine 90 is equal to 0. Let's look at an example. Let's do it. Well, I'll tell you what, let's make it specific, but then we'll make it general. Suppose we have some charge, Q, that is 3.0 microcoulombs. And we're asked to find the electric flux through a sphere where we have a radius of 0.20 meter. And I didn't explain this very well, but the sphere surrounds it. So here's Q. And here's a three-dimensional sphere surrounding it. And that Q is actually supposed to be at its center. And I didn't draw a very perfect sphere, but pretend I did. So there's our sphere. We know that the electric field radiates out every direction and would, in fact, if you stop and think, always be perpendicular to the surface. Now, I didn't draw a very good surface, but the electric field lines are going to make a right angle at every point. So in this case, E is perpendicular to A everywhere. Now, what's the area? Well, the area for a sphere is 4 pi r squared. That means that our electric flux is E times A for a point charge. This is a point charge. The electric field is KQ over R squared. The area, of course, is 4 pi r squared. So this simplifies that the electric flux is simply, notice the r's are going to cancel, 4 pi k q. Or if we, I don't know if you remember, when we first talked about Coulomb's law, we said that K can also be written as 1 over 4 pi epsilon naught. If I make that substitution, I get another version of Gauss's law that says phi is equal to Q, and they usually use a capital Q on it, over epsilon naught. Okay, that is Gauss's law. In words, it looks like this. The total electric flux through a closed surface is proportional to the enclosed charge. Now, the constant of proportionality can be written as 4 pi k, or the constant of proportionality can be written as 1 over epsilon naught. Doesn't matter. Either way, it's directly proportional. That means if the enclosed how do I say this? Let me rephrase that. If the net charge enclosed is 0, then I know that the flux is equal to 0. I can also use it in terms of signs. Notice I did not put the absolute values here. If Q is positive, the flux is out of the surface, and that makes sense because the electric field points away, like here. Notice how the lines of force are away, so we would think of having a positive flux or the electric field lines traveling out of the surface. If we have a negative charge, then the flux is into the surface. Let's look at an example. Oh, we didn't finish the previous example. Notice on the previous example, if we want to calculate the flux, it only depends on the value of Q. So let's actually go and we can calculate it. We know that the flux, in this case, is 4 pi k cubed. Now, I know we did that for a very specific surface, which was a sphere, because that was easy to draw and visualize. But Gauss's law holds for all closed surfaces. So in this case, we know the value of K was 8.99 times 10 to the 9th. Our charge in that problem was 3 microcoulombs. Micro is 10 to the negative 6. So the flux in that example comes out to be 3.4 times 10 to the 5th Newton meters squared per Coulomb squared. And if you just think about it for just a minute, here's the charge, Q. The flux that passes through this surface is the same amount of flux that passes through a larger surface. That flux actually stays constant. Remember, flux is equal to E times A. And of course, what's happening, if we pick a larger surface, A is increasing, but E is actually decreasing. You sometimes also see this relationship as the electric field is the flux divided by the area. Okay. The total amount of flux, however, is staying constant in that example. Look at a different. Suppose we have three charges. We have a charge of positive 5 nanocoulombs. There it is. We have a charge of negative 3 nanocoulombs. And we have a charge of negative 5 nanocoulombs. And I want to draw 3 different Gaussian surfaces. So I'll use 3 different colors. I'm going to call this Gaussian surface is a closed surface that contains those 2 charges. We're going to call that A. I'm going to do this Gaussian surface in green. It contains those 2 charges. And then I'll do one more, gold. This Gaussian surface I'm going to call C. The question asks, through which surface does the flux point into the surface? Well, the flux is basically simply the total charge over epsilon naught. So let's look at the total charge. For surface A, A is that blue surface. The net charge is positive 2 nanocoulombs. That is going to be out of the surface. Anytime you have a positive charge enclosed, the net flux will be out of the surface. In B, that's the green surface, the total charge is 0. That means there is no net flux. The flux is 0. And finally, for the C, that's our gold, we can see that the charge is actually negative 8 nanocoulombs. If you have a negative charge, you get flux into, think of those electric field lines, they point towards negative, into the surface. All right, let's look at a way we can apply Gauss's law to determine some charges on some conductors. This is section 17.9, charges on conductors. Okay, remember, the electric field inside a conductor is always 0 for electrostatic conditions. So, suppose I have a solid conductor with some arbitrary shape. The shape of this solid conductor is not terribly important. Here it is. It's just a strange looking thing. And it has some net charge Q prime. It's a positive net charge. These charges are going to distribute over the surface like this. Tend to distribute a little bit more when there's a sharp point like that, and a little farther apart when there's nice kind of flatter surfaces. Okay, but they will distribute over the surface until the net force on each charge is 0. Then you've got an electrostatic condition. They're not going to move anymore. Now, if we take that and we put a hole in the middle, so I'm going to make a cavity. So there I have just an empty hole inside my surface. And I want to draw a Gaussian surface. I'm going to draw my Gaussian surface in a different color. So here is a Gaussian surface. I guess I could have drawn it solid since I'm using a different color. So there it is. Now, what do I know about this Gaussian surface? I know that the enclosed net charge is 0 at a Gaussian surface. If I don't have any net charge, then I don't have any electric field. I don't have any net charge in there. All right, let's go back. Let's add another charge. So I've got the same surface. I'm going to try to draw it where it looks kind of the same. It probably won't look exactly the same, but we'll pretend it's the same. There we go. And here's that cavity. On the surface here, remember, I already had a charge of Q prime. I'm going to put a charge of plus Q right there, a new charge. And honestly, it really wouldn't matter if it's positive or negative, but for simplicity, I'm going to make it positive. I'm going to kind of erase that little extra right there. Okay. Let's draw that Gaussian surface again. Whoops. Now remember, inside a conductor, in electrostatic conditions, the electric field is zero. So if the electric field is zero, that means that Q has to equal zero. The enclosed charge has to equal zero. We go, well, Miss Hughes, the way you drew it, the enclosed charge is plus Q. Well, what's going to happen? If I put a positive charge in the middle in this hole, it's going to attract an equal quantity of negative charge. Right? That's going to get a negative Q on the surface. Notice inside my blue line, inside my Gaussian surface, I still have a situation where the enclosed charge is zero, so the flux through that surface is zero. If this attracted an amount of charge equal to negative Q, where did it come from? Well, it came from the surface here. I now have to have a additional charge of plus Q on the outer surface. So this charge on this outer surface that was originally Q prime is now Q prime plus Q. So now we would have even more positive charge. Notice we still have conservation of charge. We added a plus Q here. So the total charge for this whole thing is simply Q prime plus Q. But all of that total charge now appears on the surface. The total charge inside our Gaussian surface is going to be, or our net charge inside the Gaussian surface is going to be zero. It's possibly easier to see if we do it with numbers. Suppose we have a hollow conductor has a net charge of 7 nanocoulombs. A small isolated charge of negative 5 nanocoulombs is inside the cavity. Okay, let's draw a picture. Here's our conductor, and here's the hole in the middle of the conductor. We know that this conductor contains positive 2 nanocoulombs of charge, and somebody came along on the inside and they added a small negative 5 nanocoulomb charge. Our Gaussian surface, I'm going to draw right here in the middle. We know anywhere in this conductor that E is equal to 0, which means what? The enclosed charge is 0. The only way my enclosed charge is 0 is if I get a positive 5 nanocoulombs on the interior surface here. Remember, this is hollow. That way, you have a negative 5 nanocoulomb charge that was put somewhere in the middle. We'll draw a little, draw a little dot for that charge. Here's that charge right there. It's that dot. It's negative 5 nanocoulombs. I know the enclosed charge has to be 0, so there must be a plus 5 nanocoulomb charge in that surface. Where did that charge come from? Well, it came out of this conductor. What does that mean? That means conservation of charge says if I take positive 5 out, I'm going to have an additional negative 5 nanocoulombs on the surface. Okay, so how much charge is on the surface? Well, positive 2 nanocoulombs and negative 5 nanocoulombs is going to leave a charge of 3 nanocoulombs on the outside. Oh, nope, I misread the problem. Well, I didn't misread the problem, I wrote down the wrong thing right here. Okay, I may have confused people. The hollow conductor has a net charge of 7 nanocoulombs. I don't know why, I do know why I wrote 2, I looked at my picture. A small isolated charge of negative 5. Well, if you put a negative 5 in here, that negative 5 is going to attract a positive 5 nanocoulombs to the interior surface. It's going to try to create that 0 net charge. Okay. The result is, on the surface, you end up with a net charge of 2 nanocoulombs on the surface. Essentially, when you have this situation, it behaves as if the total charge is on the surface. 7 nanocoulombs plus negative 5 nanocoulombs gives us a net charge of 2 nanocoulombs on the surface. We know that any point inside this conductor, the electric field will be 0. This idea is used, it's often called a Faraday's cage. It's used to protect a lot of delicate equipment. It's not a surprise that most electronic things like computers are housed in metal boxes. By surrounding them with a metal conductor, it will protect what's inside from external electric fields. Okay, that finishes up chapter 17.